Lecture 24 covers section 7.9. At the end of today's lecture, you should be able to construct an integrator and differentiator circuit using op-amps and capacitors. To begin, an integrator and differentiator op-amp are circuits used to integrate or differentiate a signal. For instance, acceleration is your second derivative of displacement. So we can integrate the signal to get velocity, or we can integrate it once more to get displacement. Conversely, we could take displacement and differentiate that signal to get velocity, and differentiate once more to get acceleration. The differentiation process introduces a lot of noise into our system, and thus integration is preferable. These circuits can also be used to solve differential equations, and they can simulate physical dynamic systems. To begin, let's look at a differentiator. A differentiator is different than an inverting op-amp in that we replace our input resistance with a capacitor. That is, Vn can change as a function of time, and Vn provides a voltage potential across our capacitor that drives our input current In of t. Now, to understand how the circuit works, we want to relate our input and output voltage. To do such, we're going to apply KCL at node A. At node A, we have In entering, we have I1 and IF exiting, where IF is our current going through our follower resistance. We're going to assume I1 is equal to 0, for we're assuming this is an ideal op-amp. If we substitute in the expression for current through our capacitor and resistor, we have our input current being equal to capacitance times the time rate of change of our voltage, where our change of voltage would be Vn of t less V1, where V1 is equal to 0, for V1 is equal to V2, and V2 is connected to ground, and our current running through a resistor is V1 minus Vout per RF. Thus, we can say our capacitance times the time rate of change of our input voltage is equal to the negative of our output voltage per our follower resistance. Thus, our output voltage is equal to minus R sub F times C times the time rate of change of our input voltage. That is, we are differentiating our input signal and multiplying it by a constant minus RC. An integrator differs in that we replace our follower resistor with a capacitor, and then our capacitor that was upstream to node A goes back to a resistor. So if we want to determine the characteristic of the circuit, we once again have to apply KCL at node A. At node A, we have In entering through our resistor, and we have I1 and I sub C exiting. I1 is going to be assumed 0. If we substitute in our expressions for current through a capacitor and resistor, we see In is going to be Vn as a function of time less V1, where V1 is equal to V2 and V2 is equal to 0 per our input resistance. And our current running through a capacitor is our capacitance times the change of our voltage with respect to time. Our change of our voltage would be V1 minus Vout. Or we can say Vn per Rn is going to be equal to capacitance times the time rate of change of our output voltage. If we solve this in terms of our output voltage is going to be equal to minus 1 per Rnc times the integral from 0 to t of Vn of tau d tau. We see here we're integrating our input signal and multiplying by a constant of minus 1 per Rc.